In a distributed system, names act as logical identifiers. They allow us to request a specific resource, a file, a printer, or a web page, without requiring any knowledge of its physical hardware or network address. These identifiers are categorized by the information they carry. Pure names are uninterpreted bit patterns that reveal nothing about the object. Non-pure names, however, contain inherent data, often pointing to the object's location or its organizational home. We can parse a standard URL into 3 distinct identifiers: host name, port number, and path name. Each triggers a different resolution mechanism. The host maps to an IP via DNS, the port identifies the server process, and the path name locates the specific file. Building a global name service to manage these requests requires meeting several technical constraints. The service must ensure global uniqueness, handle high request volumes, and provide fault isolation so a single server failure doesn't disrupt the network. The structure of the namespace itself determines its capacity for growth. Flat naming spaces are inherently finite, restricted by a maximum name length. Hierarchical structures bypass this limitation, allowing the naming space to grow indefinitely through nested domains. Naming provides the logical link between a user's request and a network resource. By decoupling an identity from its physical location, a system remains functional even when hardware moves, establishing a precondition for growth. This graph illustrates a hierarchical namespace. It branches from a single root node through intermediate directory nodes, ending at data-storing leaf nodes. Following a path resolves a name like /home/steen/keys. The system also supports aliases, where multiple paths lead to the exact same node. As a network expands, a single centralized server cannot hold this entire graph. The sheer volume of entities would overwhelm it, creating unacceptable latency. To manage this scale, engineers utilize 3 optimizations. They partition data across multiple servers, replicate those servers to ensure availability, and use caching for local lookups. These 3 optimizations allow a naming system to handle the massive volume of entities found on the modern internet. They transform the naming graph from a theoretical model into a functional, scalable architecture. The domain name system, or DNS, is the real-world implementation of these concepts. It functions as a distributed database and an application layer protocol that translates human-readable hostnames into IP addresses. Distributing this database is a structural necessity. A centralized model could not handle the global traffic volume, and the distance between users and a single database would lead to high latency. The DNS namespace is partitioned into 3 distinct layers: the global, administrational, and managerial layers. The global layer contains top-level domains like .com and .org. The administrational layer includes organizations, while the managerial layer handles local zones at the network edge. If a local name server cannot resolve a name, it contacts one of 13 root name server clusters positioned globally. These root servers act as the ultimate referrers, pointing the client toward the correct authoritative server. Each layer has different operational requirements. Managerial nodes require immediate updates and near-instant responsiveness for local changes. Global nodes, which change less frequently, rely on lazy update propagation and extensive caching. This tiered architecture directly addresses the requirements of scalability and fault isolation established earlier. By separating the layers, the system ensures that local updates or failures do not compromise the stability of the global hierarchy. Name resolution is the active process of navigating these layers to find a specific IP address. The standard method in DNS is iterative navigation. In an iterative query, a server either resolves the name or refers the client to another server that is closer to the answer. To resolve .cs.vu.nl, the client first queries the root, is referred to the NL server, then the VU server, and finally the CS server. Throughout this exchange, the client's resolver manages the state, following each referral until obtaining the IP. In recursive navigation, the contacted name server takes on the search burden, querying the next server on behalf of the client. The query moves down the hierarchy to the leaf node, passing the final answer back up the chain. The primary benefit of recursion is that intermediate servers can cache the results. If a different client later requests the same address, the server can provide the answer immediately without a new search. Comparing the communication costs, recursive navigation reduces long-distance client hops by localizing the queries between servers, as shown by the server-to-server arrows here. Despite these benefits, standard DNS queries remain iterative. Full recursion would place an overwhelming processing load on the root servers, which must handle requests for the entire internet. Selecting a navigation method involves a trade-off. System designers must choose between minimizing the client's network latency through recursion or protecting high-level servers from excessive processing loads. To understand how these queries are executed, we must look at the data packets exchanged between servers. A DNS message begins with a 12-byte header, including an identification number and authoritative flags. Following the header are variable fields containing the questions, the resource record answers, and any additional authority information. Every entry in the DNS database is stored as a resource record, or RR. This is a strict tuple containing a name, a value, a record type, and a time to live. This database excerpt shows how different records populate a zone. A Type A record maps a host name to an IP. Type NS identifies the authoritative name server. MX points to mail exchanges, and CNAME defines aliases. The strict, lightweight structure of these records enables the high-speed mapping required to keep internet traffic moving efficiently across the globe. DNS is optimized for translating a known name into an address. However, it cannot handle descriptive queries, such as searching for a resource based on its attributes rather than its specific name. For these tasks, we use directory services, like the X500 or its lightweight version, LDAP. These act as search engines, allowing users to find system entities based on their unique characteristics. The architecture consists of directory user agents that submit queries to directory service agents, which manage and search the underlying data. Data is organized into a directory information tree. It is a hierarchical model that branches from broad categories like countries and organizations down to specific departments and individuals. This tree structure, combined with the detailed node information it contains, forms the directory information base. A single entry in the space is far more detailed than a DNS record. For a person, it might store their common name, surname, phone number, employee ID, and multiple email addresses. Users access this data in two ways. A read access provides an absolute name to retrieve specific attributes, while a search access is used to discover nodes dynamically. During a search, the user provides a starting point in the tree and a Boolean filter. The service agent then evaluates every node in that subtree and returns only the entries that match the criteria. DNS provides the rigid, invisible scaffolding that routes global network traffic. But for the human-centric tasks of discovery and resource management, systems like LDAP provide the necessary overlay to navigate the complex data within that network.